ഇതിലായിരുന്നു ഇതേ ഉള്ളൂ പറ്റത്തുള്ളൂ. ഇതേ പറ്റത്തുള്ളൂ. ഇത്
Good afternoon. My name is Sakul Murali. Today we are presenting about the statistics of chaotic attractor. We know about the chaotic attractors. I briefly explain about chaotic attractors. The set of points of a dynamic system evolves towards characterized by sensitivity to initial conditions and predictability. Because it's mainly sensitive to its initial condition and it is unpredictable. Then it shows sensitive depends on initial condition. This means small changes in initial condition can result in high variations or large variations. Then irregular n-bounded trajectories means the path can appear in not in a regular way. However, their behavior is in between a range of certain range. Then non-periodicity with a structured form. It does not repeat any periodic manner, but it is in a structured form or in a structured pattern. Then it is the importance of the chaotic attractors or the applications may be seen in used in understanding complex systems, applications in weather prediction, modeling financial markets, neuroscience, and brain activities.
തുടരിലാണ് ഞാൻ പറഞ്ഞത്.
Simple chaotic attractor picture to show what is chaotic attractor. It is starting there is an initial point that it is irregular, bounded, and sensitive. Depends on initial condition, not periodicity. But there is a pattern that's formed around this. This is just for picture.
Yes, it's because of the butterfly effect. If small flap of butterfly wings can in Brazil can cause a tornado. Like that's the saying for butterfly effect. That means small tiny flap of butterfly wings or small tiny outcome. And that's what chaos is. But Lorentz attractor's shape was very close to that of the butterfly. So therefore, one of the wings is given to the butterfly. Therefore, in internet you get
some of the statistical measures used to study chaotic attractors. There are so many statistical measures from that you have to take. Some of them are Diaphragm exponent, which measures how quickly nearby trajectory diverges. So it is also called hallmarks of chaotic behavior. It is the fractal dimensions, which quantifies the complexity of the attractor's geometry. And it also measures the roughness or irregularity of the system's state in space. Then it is the entropy, which measures unpredictability or randomness with the attractor. It is used to quantify the rate at which the new information is generated and not. Then it is correlation function. Studies temporal coherence, showing how quickly points in the attractor become uncorrelated. In this system, future states are less predicted as the time progress. That we are using correlation function. Then it is Poincare section. It reduces the dimensionality by capturing intersections of trajectories with a lower dimensional space. It is easier to compare compute statistical measures such as periodicity, density, distribution of points within attractors. Then we have to look upon Liopold exponent. It is a measures how quickly nearby trajectories diverge in a chaotic system. And it also gives how sensitive to a initial condition, and it helps in measuring the exponential divergence rate. Then it is the positive Liopold exponent. It means that 2 points start very close to each other in a system. At the end of the over the time they apart. This is the equation for Liopold exponent, that is lambda is equal to limit t tends to infinity 1 by t ln modulus dx of t divided by dx of 0. Dx of t is the distance between two trajectories at time t. These are the figures of random attractors found using Liopold exponent. Then the lambda value is less than 0. It's stable, it's equal to 0, it's periodic or quasi-periodic. Then it's greater than 0, we can say it's chaotic. Then the next method is fractal dimension. If fractal dimension offers a way to quantify the roughness, complexity, and scaling behavior of attractors, then it is also used at how it changes at different scales, understand how it might behave in the future states. That's how its structure behave at different scales, how predictable or unpredictable the system might be. Then the sum of the methods to calculate the fractal dimensions are box counting method, correlation dimension, Liopold dimension, and the Kaplan-York conjecture. Then the under the fractal dimension, there are two methods we have to discuss. That is box counting method. Box counting method. This method covers the attractor with the small boxes of certain sizes and count how many boxes are needed. By repeating this, we can find the fractal dimension. The equation is n of epsilon is proportional to epsilon raised to minus b. Here, the n of epsilon is the number of boxes covering the attractor. Epsilon is the box size. As you can see in the figure, how many boxes is needed for to convert a fractal. Then it is correlation dimension, which measures the correlation between points in the attractor. Then the equation is given by C of R is proportional to R raised to D. The C of R is the correlation function. R is the distance between the points. In the figure, you can say the point is encircled by the red circle can be calculated from the its bounded region circles. Next, our teammate.
Now let's look upon Poincare maps. Poincare map is one of the statistical measures that helps to simplify chaotic systems by revealing its patterns and structures within them. In chaotic system, tracking every detail can be more complex since they are having high complexity and unpredictable behavior. So what Poincare map does is it reduces the dimensionality by only capturing the specific points to show a 2D pattern instead of going through the 3D pattern. For easy understanding, let's look upon a pendulum moving as it swings. Instead of considering the whole swing, just look upon one point. It will give the simpler chaotic what it's doing over and over again. For understanding its pattern, just look upon one point and it will give the repeating pattern or loop. It never does the same thing twice in that point, it shows a chaos. And the figure shows that a 2D map and trajectory passing through it, and the point where it intersects is marked. Next is the recurrence plot. Recurrence plot is like a picture that shows when something comes back to a similar spot in the movement or pattern over time. By analyzing recurrence, scientists can calculate various measures like recurrence rate, determinism, and entropy. And the figure shows the graphical representation, grid-based visualization of when the system returns to similar states over time. And its temporal coherence and the correlation of chaotic attractors. Temporal coherence is all about how long the trajectories remain within the chaotic attractor, similar to each other over time. Usually, chaotic attractors doesn't last long as trajectories quickly lose correlation due to the sensitivity as initial conditions. Correlation function in chaotic attractors. Correlation function measures how related systems state at its initial point as it to its final or a future point. And the equation given as C of t is equal to average of x of t into x of t plus tau minus average of x of t plus tau, where x of t is the system's state at time t and x of t plus tau is the system's state at t plus tau. Tau is the time delay, which is the difference between t and t plus tau. And next, the interpretation that we get from this equation is when the t of tau is large, the correlation between x of t and x of t plus tau is high. And when the c of t is small or zero, there is no correlation. And the other case is when the value of c of t decreases as t increases, this shows chaos. The first figure shows the correlation over time, which shows the no. Instead of psi, it is just CF x of t. In the equation, it's taken x of.
Yes. Just show. What are you taking on the figure and what are you taking? Both have to match.
Showing the decay pattern, how indicates how quickly the trajectories lose correlation.
What do you see here?
Correlation.
See and from the see, you are telling that C of tau is the correlation function in chaotic attractors, so it measures how fast it diverges. Here you are saying if C of tau is large, then yes, xt and xt plus tau are. If C of tau is small or zero, xt and x tau have no correlation. Okay. Now, due to all these points, I want to see from your plot what is the C value. C value is like, as you can see, it is decaying to zero. Psi of t is decaying. I am confused. Since it is decaying to zero, is it equilibrium? As you know, C of tau is decaying, that means it is. Well,
See, that is t minus 1.
yeah, real number means minus infinity. But what should be this value of? What should be the value of C?
See,
Why? See, you are saying 0. That means no correlation at all.
No, in 200, tau, when tau value reaches 200, it becomes. When tau value reaches 200, C of t becomes 0.
So you are admitting that psi of tau is nothing but C of tau.
C of
Yes.
Yeah.
So C of tau it is approaching to 0. What does it mean?
decay, no correlation,
Correlation. Then,
decay.
but you did not write anything there. So it is chaotic. It decays to 0. C of tau decays to 0. Now is it chaotic or periodic or equilibrium?
Chaotic.
No, okay.
While making the slide, you should follow this pattern. Otherwise, you will have things like this.
Next is entropy. Entropy is the level of unpredictability or randomness in how the system evolved over time. A high entropy value shows reflects a more disorder and indicating the predicted future become more impossible to do, and due to its sensitive dependence to initial condition. From this graph, we can see that the peak values shows the peak values are unpredictable because of the high entropy value, and the valleys are predictable because the entropy is less there. And the equation given is h of x is equal to minus sigma equal to 1 to n p of xi log p of x, where p of xi is the probability of occurrence of this state. I explained it. In this figure, the peak values were having high entropy, so it is unpredictable, and the values having less entropy, so predictable.
If we get 1.5, the KV reaching.
We not bother about that. Every
No. Putting the time and entropy. Good afternoon. I am Irene. Next, we talk about the time series analysis for chaos. Time series analysis helps uncover the underlying dynamics and statistical properties of attractors. It involves studying the values of a system state variables over time. When applied to chaotic system, it helps to reveal underlying dynamics that appear random pattern. By examining sequences, when we look through an example of law which is defined by these equations, by analyzing this graph, we can on time on x-axis and x variable on y-axis, we shorten behavior through this graph. Next, we move on to some of the techniques for time series analysis of chaotic system. First is autocorrelation. Autocorrelation which identifies patterns and dependencies over time. It measures how a variable correlated with its past values determine the time lag where patterns recur. By analyzing the first graph plotted here, we can identify lags on x-axis and values on y plots. We can identify the lag that occurs between the patterns. Next is phase space reconstruction. Phase space reconstruction uses time series data to reconstruct a higher dimensional phase space. This is useful for visualizing chaotic attractors from one-dimensional data. Here we can look to the second graph. We can identify the space reconstruction. Next is delay embedding. The gap between are representing lags.
And some are positive, some are down. Is there zero?
Negative.
Negatively correlated.
And positive.
Correlation.
That is negative and positive correlation.
Positive correlation and negative correlation. Dependence between the past values. How a variable correlated with its past values with a positive value, it becomes positive with its negative value. Next is delay embedding. Delay embedding uncovers underlying attractive structure, which means construct space using delayed version of the time series. By looking to this plot said, by plotting the time series against itself with a time delay, we can reconstruct the attractive structure even with a limited observable variable. Next, we are moving on to the statistical invariance and ergodicity. First, we discuss about statistical invariance in chaotic system. Statistical invariance. It means that as we observe the chaotic attractor over a long period, the statistical space remains consistent, which this is due to an invariant measure which provides a stable over the attractor. But this is the mathematical representation. It means that average time, average value of f of x over the invariant measure remains unchanged as time progresses to mu t. Next is ergodicity in chaos. Over a long enough period, a trajectory on a chaotic attractor will eventually visit all regions to their probabilities. It means ergodicity is a time averages of a function or a single trajectory equals the ensemble average over all possible states. This is ergodicity. Its equation, mathematical representation is limit t tends to infinity. Integral 0 to t f of x t dt equal to integral f of x du mu of x. Its equation shows that the time averages of f of x over an infinite time equals the average over the invariant measure mu of x. We can identify the difference between structured, random, and ergodic attractors. Because in ergodic, they're proportional to the all are equally proportional to their problem values. In random, they are distributed over the random variables, and structured, they are in structure arrangement but not ergodic. Thank you.
Myself, Nikhil. So, coming to the topic probability distribution of attractors. So, probability distribution on attractors provide a statistical framework to describe the long-term behavior of trajectories. Since chaotic systems are unpredictable, so at the level of individual trajectories, probability distributions allows us to understand where the system is likely to be found over time. So by looking the system over a long time, we can see where it tends to spend the most time. This gives us a probability distribution over the
based on statistical map. This statistical map is known as invariant density. So it means invariant or unchanging probability distribution that describes where the system is likely to be. Okay, so to find this invariant density, we use something called Frobenius-Perron operator. Okay, let us discuss in detail. So let us start from a uniform. Let us start from a uniform density. Okay, with the initial condition. Okay, from 0 to 1. Okay. This is a density function. If we apply the function to each point, it will give another function that is different from this. Okay. If we apply the function to each point on the first map, it will give another map which is differently distributed. We will apply this process repeatedly. So first we start from an initial condition with a density function, and we apply each point the function again, and it is differently distributed. So further, we apply this function over period, then it will converge to some kind of a density function. That is last one. We apply the function over each point, and this is the invariant density. Invariant density. If we apply the same function to each point of this, it will give the. So ultimately, the map is defining an operator which, when applied on a density function, it will give another density function. So invariant density is when you operate on it by that operator will give the same invariant density. So it is a fixed point of that operator. This called as Frobenius-Perron operator. So suppose it is defined by the function t. So suppose it is defined by the function t, which when operated on row of x at the nth iterate, it will give a row of x at n plus 1 iterate. And the invariant density we can
get the invariant density when this operator P is fixed. So invariant density term is get when the operator P rho star is equal to rho star. This is what invariant density. So from this figure you can see the first one, and we apply the function on each point. We finally got the invariant density.
Function is applied.
Function is applied.
No, each row,
Each
row. Function is applying to every point.
No, what I'm asking is, tell me about this. What does this mean?
First,
Then we apply the same function on. Then it goes to here, and the last one is the invariant density.
Like this.
Yes,
Labeling is wrong.
Why sudden changes are obtained like
Yeah,
it seems
that
it's a
is
very
chaos.
unexpected sudden.
chaotic magic.
So what kind of function are everything functions?
Yes, the function will be called. Yeah.
Is it a 1D map? Is it a 2D map? Is it a 1D?
Sure. So here are some practical uses of chaotic attractors in weather and climate. The atmosphere is chaotic. So long-term weather predictions are, but with the statistical analysis can help identify probable weather patterns. And in financial markets, markets are often be chaotically due to high sensitivity in initial conditions. So chaotic attractors analysis helps in identifying statistical patterns that. And in medicine and biological rhythms, many biological processes such as neural activities display chaotic behavior. So by analyzing chaotic can better understand and predict irregularities, which can help in diagnosing and treating conditions. And in engineering systems, certain systems such as mechanical vibrations or electrical circuits exhibit chaotic dynamics. And with these systems can help engineers. And in ecology and population dynamics, in ecological systems, including animal populations, are often chaotic. So, with this chaotic attractor analysis, we can predict possible long-term behaviors of animals and their populations. Okay. Conclusion. So, while concluding,
Minus is there. I don't know.
So, in conclusion, even though chaotic attractors systems are highly sensitive to initial conditions, they still follow long-term patterns that we can study statically. So, by examining the probability distributions over these attractors, we gain insight into the regions where the system is found over the time. This approach allows us to go beyond That's for conclusion.
Conclusion.